Hello, I'm going to introduce the next speaker. She's a PhD student at the Institute for Robotic Language and Communication at the University of Amsterdam under the supervision of Willem Sudema. Her research is focused on understanding how recurrent neural networks can understand and learn the structures that occur in natural language. And last but not least, she's also a national champion in pole dancing in duo. So let's welcome Dieuwke Hupkes.
Thank you for this nice introduction. I'm very happy to be here today. And indeed, I think that every researcher should also have a different passion aside from whatever he's researching. And for me, that's pole dancing. So thank you also for mentioning that. But today, let's not talk about pole dancing. Let's talk about my other passion, which is language, and in particular, structures in language. So, actually, since I can remember, I've always been very fascinated by the types of structures that we see in language, and in particular that they are so beautifully complex. And at the same time, we can all learn them, and we seem to sort of agree on which things are grammatical, which things you can say, and which things you cannot say. Now, when I learn a new language, which I also really like, one of the first things that I always do is I start to learn some grammar rules, in particular verb conjugations. I really like verb conjugations. And why I like that is because I learn a couple of words, and I learn a couple of verb conjugations and some basic grammar rules, and all of a sudden I can say a lot of things already, and that feels very good. Of course, afterwards comes the part where I realize that to then get to a conversational level, it takes a lot more pain and effort, but also that we're not going to talk about today. Today I want to talk about structures in language. And the way that I presented it until now, it seems maybe I'm talking about syntax, but actually what I'm talking about is the way that we form meanings of sentences from sentences using structure. And some people call this compositionality or hierarchical compositionality. And the way that I want to talk about this today is really in the most abstract, generic level, not necessarily linked to any particular language. And how I will explain to you with an example sentence. The scientist who wrote the research paper jumped with joy. Now, unless you've had me give a presentation before, you've probably never heard that particular sentence, but still, you can all understand, I hope, what it means. And the reason that you can understand what it means is that you know the words in the sentence, and you know how to compose them, you know the rules, so to say, to combine them, to know also the meaning of larger chunks. This particular sentence, we can say, consists of two parts. We have the subject, the scientist who wrote the research paper, and what the subject is doing, jump with joy. Now, and here comes in the word hierarchical that I was mentioning before, these subparts themselves also consist of smaller parts. So the scientist who wrote the research paper consists of the scientist and the embedded class who wrote the research paper. Now, from a classical linguistic viewpoint, we can also put names on these notes here. So we can say the scientist is a noun phrase, the research paper is a noun phrase, we can combine these things to make another noun phrase, getting a noun phrase inside a noun phrase. And we can say that there are some rules that tell me what I can do and what I cannot do. So, for instance, I can combine a noun phrase with a verb phrase, and then I get a sentence. Now, irrespectively of whether you think that these rules are a reality either in the brain or if language is actually generated by some system, these kind of systems describe language very well. And this puts me in a kind of a difficult situation, because when you look at our brain and our humans and the means that we have to our disposition, it is very unclear how that would work, because it's not that in our brain we have symbols and rules. So the question that I'm asking myself is, how are these two views reconcilable? So how do our brains represent language if they don't have rules and symbols? I am not a neuroscientist. I think we will get some interesting talks later on neuroscience, but I'm a computational modeler. So the way that I'm going to approach this question is by trying to do some computational modeling and hope that this helps me to understand the underlying system. And in particular, the type of model that I'm using are recurrent neural networks. Now, in the beginning, I also considered putting some equations on the slides, which during the previous talk I was wondering maybe I should have done it, but instead I decided to go for just a schematic here. So I don't know how familiar you are with artificial neural networks, but for this talk, the most important thing you need to know is that neural networks are basically a collection of artificial neurons that are connected with each other. In this case, in the recurrent neural network, what it does is it takes an input, it processes it with its internal connections, it generates an output. Then it takes this state to for you it's that side, next step, takes another input, processes it, generates an output. This is the most simple form. This doesn't work super well, but when you add some gates, it does start to work super well. And what these gates are doing is they modulate the information flow. So they say these neurons maybe can only be talking to each other in a certain situation. So you can see this as doors that open and close, depending on the current state of the network. And this makes this network much more suitable to model long-distance relationships. Because for instance, say that you have a network that needs to keep track of subject-verb relationships, it means that it can be that there is a particular neuron that when the subject comes in, it says, that's my job, I'm going to remember now that this is a singular word. And then it closes all these doors. It doesn't take any input anymore until the verb comes in, and then it knows to open. And this makes it way easier to model long-distance dependencies than when there was this continuous connection that always meant that a neuron had to do some processing in the next step. The question, though, is how do they do this? So these models, you may have realized, are really kind of taking over the state-of-the-art in natural language processing. So they're the models that Google use. If you use Google Translate, it will be a model like this. And it turns out that they're really, as these symbolic models, from a different perspective, also a quite adequate model of natural language. But they're also black box models. They learn themselves, we just throw some input, we let them update themselves, and they work very well. But how do they do this? And this model, as you may have realized while I was talking, it's not that it's really like the brain. I want absolutely to make no such claim, but it has some properties that it shares with the brain. So it needs also to process its input incrementally in linear time, and it's also just a bunch of neurons that are connected, units, let's call it, that do not have any explicit means of representing symbols and rules. So the question that I want to focus on today is how can hierarchical compositionality be processed incrementally in linear time by an artificial neural network? I'm going to split this up in two questions. So first we want to establish that they actually can do this. So can recurrent neural networks represent hierarchical structure? I will look at two different settings. So I will look at this in a clean setting with an artificial language, and then I will move on to dealing with natural language. The second question is, how do we understand if and how they can? As I said before, these models are sort of black box models that get an input and give you an output. And whatever they're doing inside, it's not very, very easy to study, actually also much like the brain. So a second question that we're asking ourselves, and these lines will go a bit in parallel through my talk, is how do we understand if they can? And in particular, I will look at some studies that are based on their behavior, so if I give them a certain input, what kind of output are they giving? And some that really look inside and look at their representations. So why do I want to study hierarchical compositionality in an artificial language if I'm actually interested in the type of compositionality that occurs in natural language? The reason for that is, and this is somewhat related to what I was saying before that, in the beginning it seems easy to learn a language, but then a whole bunch of other things that come in, is that natural language, aside from structured, it's also quite messy. So there are many structures that are clear and that we understand, but there are also many parts that fall outside of that, maybe there are exceptions, and this makes it difficult to study compositionality in its natural habitat, so to say. Then a second reason is that while we are very good at extracting the meaning from many sentences, these meanings are not very well defined. So it's not easy to understand if a network actually understood. I cannot give it a sentence and ask, do you know what this means? And with an artificial language, we can go around this, because I can create an artificial language that is very hierarchically structured, the meaning is compositional, easily defined, and I can ask the network if it knows what it means. The language that I'm looking at is called the arithmetic language, and it contains words for numerals, so 1, 5, plus 5, minus 5. It contains words for the operators plus and minus, and it contains words for parentheses. And the sentences that it has look something like this. So bracket 5 minus bracket 2 plus 6 bracket bracket. And as you see here, what is the meaning of this particular sentence? It depends on how the brackets are put. And the meaning is very clearly defined because it's just the sum of this expression. And it has these properties that we're looking for. It has hierarchical. I can make it as deep as I want. I can make it as long as I want. And later what I will do is I will make different subclasses in these languages, that in this arithmetic language, that are defined by how many numerals there are. So for instance, language 8 will be a sentence that has 8 numerals. And this means that it has 16 brackets and 7 operators. So the length of the sentence itself is actually much longer than the number of the sentence. First question, can a gated recurrent network learn this language? So here you see these different languages that I was talking about. And when I was first doing this, I was actually quite amazed that this worked at all. So what we have on this axis is the mean absolute error. So this means a mean absolute error of 2 means that the answer was 6 and the network instead predicted 8 or 4. And L9 is something with 9 numerals, as I said before. And if you think about it for a second, it's actually pretty crazy. I mean, imagine that I would give you an expression like bracket, bracket 5 plus, bracket close, but up to 9 numerals, and would ask you to then, on the spot, give the outcome without using any piece of paper. That would be pretty tough for us. So I was pretty impressed that it could do this at all. And now, there's one thing that I deliberately left out of this plot, because you may think, okay, that error bar is going up pretty steeply. And this, of course, makes sense, because computing something with 9 numerals is much more difficult than computing it with 1. So what I did to understand if this network could actually model this is I left out particular types of structures. So I trained this network to predict L1, L2, L4, L5, and L7, and I checked on all of them. And the fact that it doesn't go like this gives me the indication, so that it doesn't work on exactly the types of structures that it hasn't seen. Tells me that this network, at least to some extent, maybe it makes some errors, but has understood the hierarchical structure of this language. So far, so good. We're interested in how does it do this. Now, a first thing that you can do, I wouldn't recommend it if you can, is look at some network activations. So, contrary to the common networks that are around now, the network that I used was very, very small. It had only 15 units. With 15 units, you cannot get very far, but at least you can look at activations. I spent quite some time breaking my head over looking at this plot. I think I found some interesting things, but the main takeaway message from this plot is not go look at some activations, but this is difficult. I mean, if you check this, whether you find something is going to depend very much on your own creativity, for starters. Second, it depends on whether something is implemented in one particular unit, because if something is distributed over units, you're never going to find it. And also, the scalability of this goes down pretty quickly with the size of the network. So here I may still be able to do this, even though already just looking at 3 takes quite some time. If I have a network of 1 million neurons, there's just no way I'm going to find anything. So we need something else to look at these networks. And there's something that we're going to use that I'm going to use. I will get to that in a second, but first I will go through some symbolic solutions of solving these particular sequences. And why am I that because the solution that I'm going to present to you depends on having hypotheses about what the network may be. Now, while I take a little sip of water, I want you to think 10 seconds. If you had to solve this expression, what would you do? Tell me.
I would go inside out.
Exactly. So you would do what I would follow a recursive strategy, right? You would compute the stuff that's in the smallest bracket, then you would use that, and then you would go wider and wider until you arrive at the final outcome. Now, if you want to do this in an incremental fashion, you need to keep a stack that takes care of remembering some numbers and remembering some operators. So we see the 5, we have the 5. We put the minus, we have to see the minus, we're still good. Then we see the bracket, we're going to put the 5 and the minus on the stack, and we're going to do what Peter just said, we're going to compute what's inside the bracket. So we're at 2 plus 6, which makes 8. Then, if this bracket comes, I'm going to fetch my 5, I'm going to fetch my minus, and I'm going to integrate it with what I just saw, and I arrive at minus 3. This is not the only way that you can do this. You can also do this in a more cumulative way, and this requires still a stack to keep track of the operators, but it doesn't require a stack to keep track of the numbers. So what I'm going to do is instead of putting numbers on the stack, I'm just going to use my operator stack to compute whatever I need to do with the next number. So when I see this minus, I know that whatever is going to follow now, unless there's another minus, I'm going to need to subtract it from the subtotal that I have. So now when I see the bracket, I'm going to keep my 5, I'm just going to put the minus on the stack. When I see the 2, I'm going to immediately subtract this from my subtotal. When I see the plus, I stay in my minus mode because pluses don't change anything. When I see the 6, I'm going to also immediately subtract it. And I'm going to luckily arrive at the same answer of minus 3. Now, I'm going to use this information about the symbolic strategies to understand if this network is following one or the other strategy. And how I'm going to do this is these strategies that you see in the sequence of numbers here, they make pretty different predictions about what kind of computations this network is doing. So if I'm following this recursive strategy and I just have seen 6, I need to have 8 somewhere floating around in my representations because it's something that I just computed. In the second strategy, that's not the case because I never subtracted 6 from, I never added 6 and 2. Because I already subtracted 2 before, so the only thing I did there was subtracting 6 from my current subtotal, so there's no reason for me to have 8 in my current representation. So what I'm going to do is I'm going to use another model and see if I can predict these subtotals and also this mode of operation from the representations that I have. So I take my gated recurrent neural network, I make it process a bunch of sentences, I take all the hidden activations that it's going through, so the states of these neurons, and then I'm going to train a model, a diagnostic classifier, to predict the values of these subtotals from the hidden states. If I can do this very well, this is an indication that these things were in fact represented by the states of the model. If instead I cannot do this well at all, this means that the model probably wasn't actually computing well. So what we see here is we still have the languages on the x-axis. What you see at the end here are left branching and right branching structures. So these would be sentences. So right branching sentences with minuses are particularly difficult because it would be a sentence like open bracket 5 minus open bracket 7 minus open bracket, which means that you need to make a very long stack of operators if you're following this recursive strategy, and you need to do a lot of switches if you're following this cumulative strategy. For the left branching ones instead, they are much easier because you can always just immediately apply the operation that you have. So what we see here is that this cumulative strategy, we can predict these subtotals pretty well from the hidden states. Whereas for the recursive strategy, we're really going up. So on this plot, we have the mean squared error on the y-axis, and you see that while it stays low-ish for the cumulative strategy, for the recursive strategy, it really has when you arrive at 9, it has a mean squared error of 60, which is pretty steep, considering that I was only using actually outcomes that were between -60 and 60. Here, I also tried to predict the operation mode of the model. So this is in the cumulative strategy, whether the next number needs to be subtracted or added. And this, once again, is something that the recursive strategy, there is absolutely no reason that it needs to have that information. It's something used by the cumulative strategy. And this is predicted super well, which to me really indicates that this is more or less what this model is actually doing. So it may make some mistakes with subtracting and adding, but it knows what needs to happen with the next number. So interestingly, I'm not presenting it today, but when I did some more research about how it was representing this, I discovered that actually the cumulative strategy that I formulated was also not what it was doing. It was doing some cumulative strategy, but instead of keeping a stack of both pluses and minuses, it only counted the minuses. Because as I said before, the pluses actually don't make any difference for what needs to happen, whether this mode needs to change. And this was also quite an insight for me, because I thought pretty well about what kind of strategies such a network could be doing, and these were the two that I came up with. And when I did some research, I discovered it was doing something which was actually smarter than what I had thought of, or at least in terms of requiring least effort. So one of the lessons that I also took from this is, don't think that you can even come up with all the hypotheses. It might such a network might just do something that you didn't even think of beforehand, which of course makes it also much more difficult to find. So some intermediate conclusions that we can draw here is that these models seem to be fairly able to compute the meaning of sequences with hierarchical structure. And diagnostic classification is a very useful tool to narrow this down, because while before we had to look at activations and hope we would find something, now at least we can formulate hypotheses and quantitatively test if these hypotheses are true. There are also some other possibilities that I wanted to just mention in case you're interested in this. So you can of course do many more things with these diagnostic classifiers. You don't have to just stop at training models. So on the top is this further fine-grained analysis that I was just mentioning, where I was just simply training more diagnostic classifiers to get more information. But another thing that you can do is also you can then start to mask out some of these weights of the diagnostic classifiers to see which part of this network is actually taking care of what. So this diagnostic classifier, it connects all the neurons to the classifier that gives you the prediction. But maybe for some units, the weight that is connected to that prediction is very low, which means that they're not really very much involved in storing that particular information. So this is another option to really use them to narrow down where stuff is happening. This was something done also in another paper, so you can locate them to find important neurons. You can understand if information is distributed locally or in a more distributed fashion. And, interestingly, you can even use it to influence the behavior of the network. I'm not sure if I will have time to tell you how that works. Maybe I will. In any case, I have some slides in the appendix if you're interested. So let's move to the second part of this talk: natural language. Now, as I said before, for natural language, there are some difficulties that come in that we didn't have with these artificial languages. So, first of all, we cannot just train a model to predict the meaning because we don't know how to define the meaning. Language is more messy. So what I'm going to do here is I'm going to look at something which is called a language model. And what a language model is doing, it used to be a very useful tool also in many applications. I think it's still. So a language model predicts the next word in the sentence. So you give it some prefix, such as hi, you want to go to the, and then it predicts what's the next word. So it's trained to form expectations about what is the next word. And this is nice because there is some link here with also the cognitive perspective and about us also trying to predict next words. And also it means that I don't need any annotation. So I can just take a very large corpus and I can train a model to always predict the next word in this corpus. Now, to study this model, of course, once again, we cannot simply ask it questions. There's only one thing that this model does, and that is predict the next word with a certain probability. So what we're going to do to figure out if this model learned anything about hierarchy is we're going to use some phenomena in natural language that are generally thought to give an indication that also natural language has hierarchical structure. And in this particular case, I'm going to look at subject-verb agreement. So in English, and actually now that I think about it, in most of the languages that I ever looked at, which are all European languages, the verb in a sentence depends on the subject, and it needs to agree in number. So we have the scientist who wrote the research paper jumps with joy, but the scientists who wrote the research paper jump with joy. And already in this case, there is an embedded clause that's separating these two things, but in theory, the material that is between the subject and the verb can be arbitrarily long, which means that there is no straightforward way to model subject-verb agreement without keeping track of the syntactic structure. Because, for instance, if I take a strategy like I'm simply just going to take the last noun that I've seen and I'm going to match the number of that doesn't work. Because here, in the second case, we have also research paper and paper jump. So the old models that used to be on your phone, if you remember, there used to be T9, which would depend only on a very small window. T9 in this case would in the second sentence probably say jumps because it just seen paper and it doesn't have any further history. But these language models are actually pretty good at this. So a while ago, there was an influential paper in which they used this subject-verb agreement. They formulated the number agreement task to define if models could capture hierarchical structure. And it's very simple. You give a model the prefix, in this case the scientist who wrote the research paper, and then you check what it predicts. If it predicts a verb with the right number, you put it in the correct category. If it's wrong, you put it in the wrong category, and you simply compute the accuracy. Now, I want you to look at just the top two lines here that show that in the number of attractors is the number of intervening nouns in the middle. So this is somehow a measure of how difficult it is, because of course the more nouns there are in the middle, the more difficult it becomes to understand which is the noun that you should match it to. And what Linzen and also Gulerdava and others showed is that even with 4 attractors, this still works pretty well. So this model is fairly accurate it stays above 90% with predicting the correct number of the verb, which they took as evidence that these models really represent hierarchical structure or something. I wanted to show you a second plot that I thought was really cool, because what the authors of the second paper also did is they said, it may be that there are some semantic cues that we're dealing with here. So, for instance, I said before that your T9 model might say research paper jumps, but it probably will actually not say that, because who's ever seen a paper jump? That's a bit weird, right? So it may also be that these sentences are formulated in such a way because they are real sentences, so they are semantically coherent, they make sense. That the model is, instead of using syntactic clues, it's using semantic clues, so it can match the noun with the verb, just because this noun makes more sense with that particular verb. So what Christina Gulerdava and colleagues did to check this is they created a bunch of nonsense sentences. So they kept the exact same template, but they replaced the nouns such that from a semantic perspective they didn't make any sense anymore. And what they also did, which I quite like because this is something which is sometimes forgotten by people in our field, is they did this experiment also with humans. Because this is another thing that sometimes you don't think about. You think, okay, we know this grammatical structure, and humans should do this correctly, but the fact that you can do this when you look at it and when you're a linguist doesn't actually mean that if people are seeing these sentences in real life, they can. They can also do that. So what we see here is the red ones are the human subjects, and the blue ones the LSTM. And you see here that both of them go down a bit in the original sentences and in the non-sentences. But the LSTM and the humans are really fairly close together. And both of them, also humans, go down in accuracy when the sentences are semantically non-sensitive. Now, there are some, so this paradigm became very, very popular. So if you're interested in what neural language models can do, this is your time. I wanted to just list a few studies of other people that have also looked at different kinds of questions. So negative polarity items people have checked. This also works relatively well. Filler gap dependencies, which are studies actually of one of the speakers of tomorrow, Roger Levy. Reflexive anaphora, garden path sentences, and many more things. So this is really a booming field. Many people are checking what these models are doing, and this paradigm is really great because it fits exactly the natural habitat of these language models, so to say. But here also we have again the question, how do they do this? So they seem to be doing this, but how? I put diagnostic classification too, not because it's a different technique. We're just going to again use the same technique, diagnostic classification, but this time we're going to use it to check how these models are representing subject-verb agreement and what goes wrong when it goes wrong. So I'll skip back so you're not distracted by the results. I will just recap how this works. So in this case, what we're going to do is we're going to use the diagnostic classifiers to predict the number of the subject, the grammatical subject, from all the hidden representations. So if we have a sentence like, the scientists who wrote the research paper, we're going to make the model process this sentence, and we're going to take all the hidden representations that it goes through while predicting the next words in this sentence, and we're going to train one diagnostic classifier to, from all these states, predict the number of the subject. Now, this works quite well if you look at the sentences where the model got it right. So these are the sentences. Any bias in the article almost certainly relates to where, relates is the verb, where it actually correctly predicted that relates was singular. And as you see here, it seems that this information is pretty well represented. It just stays there. If you look at the sentences that were wrong, it doesn't. So you see, interestingly, that already in the beginning, when it sees the subject, something seems to go wrong with how the information is stored. So already at the subject, there is a lower accuracy than for the sentences where later it will be correct. But the really very big difference is when this attractor comes in. So it seems that the sentences where it's going wrong, these models are truly confused by this attractor that they've just been seeing. Now, the picture that I showed you here is on the hidden activations. This matches what I also did with this arithmetic language. This was a slightly different model, but you can, in theory, use these diagnostic classifiers also on all the other components of the network. So, as I said before, these networks have gates, the doors that decide the information flow. You can also train these classifiers on whether the doors are open or not and check if they are representing any information. So this is a two-layer network. What we see here is the bottom layer is where the information comes in, then it goes to a next layer, and there the information goes out. Generally, the lowest layer where the input comes in, it doesn't represent this very well. The top layer represents this a lot better. So it seems that the subject information is really put and stored in the top layer of the network. There doesn't seem to be a gigantic difference between the gates. So the gates are F, I, and O, forget input-output, and the hidden activations are H and C, the memory cell and the hidden activations. To be entirely honest, I'm still a little bit puzzled by why the gates are still reflecting this information so well in the case that the network is doing it correctly, because to me it doesn't seem very logical that they would keep track of this information, but what we can see mostly is that the information seems to be represented all over. It's represented better when the sentences are correct, and it's represented best in the hidden and the memory cell. Now, the next thing that we did is we trained separate diagnostic classifiers on separate time steps. And this is a technique which is also known from neuroscience. You can make a temporal generalization matrix that gives you information about how much information changes over time. So, say that I see the subject, I put this information somewhere. If I keep this information during that I process the rest all the time at the same time, this means that if I train a classifier at the point that the subject comes in, and then I test it anywhere else in the sentence, I should still have a high accuracy. If this information, instead I put it somewhere when the subject comes in, but then I move it somewhere else and then I continue, then this classifier that I trained on the first time step when the subject came in, it doesn't necessarily have to have a high accuracy here because I moved the information. So what we did here is we trained diagnostic classifiers on every time step. So this was a sentence, these were sentences with a fixed sort of template. There were always equal number of words between the subject and the verb. And what you see here in this plot is on the x-axis we have the training time. So 0 is the classifier which is trained on the subject, 6 is the classifier which is trained on the verb, and the other classifiers are the ones that are trained on intervening material. And what you would expect, and you see this also, is that the diagonal has all very high scores. Because this just says if I train a classifier on the subject, and then I take another sentence, I use the same classifier, can I predict this? This works very well. But what we see here, which is very interesting, is that there seems to be a shallow and a deep representation of number information. So the classifier trained at the subject time step, it doesn't work very well when you look at other time steps. So this is what you can see in the first column. We have we have a high number here, but then if you start training it on the other ones, it doesn't really work very well. And particularly if you train it on the attractor, it gets a very low score because it still uses the same mechanism, but at that point, this mechanism is actually being used for the attractor. Whereas, if you look at these classifiers trained on time step 2 to 5, and you look at the scores in this entire block, there is actually not so much difference in these scores, which means that once the information is moved, it stays there for a bit until the verb comes out. And we took this as evidence that there is a deep representation of the subject-verb, of the number agreement, which is in this green block over here, and a shadow representation, which we see in this first one. Okay, so in the interest of time, I think I'm going to skip the interventions bit, but once again, if you're interested, please come chat with me later. So I wanted to show you some other things that we can also do in the interpretability scene. Because of course, diagnostic classification is not the only thing that we can do. So another very nice study that I also already mentioned before is one where we ablated units. So this is something that I guess would also be cool to do with the brain, but we don't really get to do that unless we find someone who already has some region in his brain lesion. But with recurrent neural networks or artificial neural networks in general, we have no such ethical issues. We can just ablate whatever neuron we want. And if you have a lot of computation power, which luckily we had for this particular project, you can ablate all the neurons individually and check what's going to be the outcome. Now, what we see here is we have also, we have a bunch of sentences with a fixed template, and what these different conditions indicate is what the intervening material is like. So, for instance, non-PP means that the intervening material is a prepositional phrase and it contains a noun. So that would be something like I was thinking of the Nazi word, but no, the Dieuwke with the computer. So there's a prepositional phrase and it contains a noun. And there's an APP which is a similar construction. construction, but it contains a name, and then there are some also where there just simply, there is no embedded clauses, but there's just a bunch of adverbs in the middle. And the most interesting conditions in this case are the ones where there's actually an intervening noun, because these are the supposed attractors. And something very interesting came out of this study, which is that this particular network, which is actually the same network as the one that I showed you in the previous slides, has one single unit that represents singular and deals with cases of singular, and one single unit that deals with the plural cases. And this, to me, was kind of a crazy finding, because these networks are generally assumed to represent everything in a very distributed way. But in this case, that's not true. And we ran this also for a bunch of other networks. It's not that it was just this particular network. It seems that these things are represented in a very local way. And how do we see that? We see, so here we have the full accuracy of the model when it just has all the neurons. And you see that on all these cases, it does pretty well, except here there is one where it's not doing so great. So this is has a plural subject and has a singular noun as an attractor. And if there is a dash, it means that ablating didn't have any significant effect on the performance. And what we see here is that if we ablate this unit 988, which is a unit in the top layer of the network, like we also found before, then most cases in which the most difficult cases in which there is a singular subject, the accuracy goes down by a lot. Similarly, for the plural one, actually there it's even more convincing, because it's for pretty much all the plural cases with attractors. The accuracy also goes down a lot, while it doesn't have any effect on the prediction of singular verbs. And as I said, this is very interesting, because it can give you really information about how this network is representing things. And another thing that we found, and this also explains why there is no effect on these cases where the verb is directly following the subject, is that for shorter distances, this is not encoded in a single unit, but there is a group of units that's taking care of this. Now that we have identified these units, we can actually also have a look at them, and I wanted to give you an example of the one that encodes singular subjects, because it actually does exactly what I told you in the beginning that it could do. So when the verb comes in, it opens its input gate saying, come on with this information, I want to store it. Afterwards, it closes the input gate and it says, I want to just keep my information. And now this is something that we could of course only do because we already found this unit, because it's not something that you can check for every unit in your system. But given that you found this unit, it's pretty nice that this network actually follows almost pretty accurately what you would write out if you wanted to implement it yourself. Now the last thing, and there is going to be another scary plot here. So I don't know if any of you is familiar with attention plots, maybe not. It's something that they use a lot with in machine translation. So in my field, attention plots probably means something different it means for many of you. So what this plot tells us is that this is a particular technique called contextual decomposition, and it can map out, using the network dynamics, what is the impact, what is the influence of a particular word on a particular output word. And what you want for subject-verb agreement, for instance, is that if the verb is generated, this depends on the subject, right? So you can in this way check, is it really using this information of the subject? So this is just one example plot that we generated. So you have here the input. So what you see here is that when the network generates the word nose, it actually depends on the word doctor, which is good, because it means that it's not using semantic information or other types of information, but it took this information from doctor and it generated nose. Whereas when it generates null, it doesn't depend so much on doctor, but instead it depends on, it took this information from dogs. And one thing that we found here, and this is pretty new work, is that it seems that this network actually has some sort of default reasoning. So you cannot see that here so well because there is a nose and no, but what you can see is that when it generates nose, it doesn't actually only depend on doctor, it depends very largely also just on the initial state of the network, which is kind of strange, right? Because the initial state of the network knows nothing about the sentence at all. Why does it do that? It does that because it just by default predicts this, and only when it sees evidence to predict the other one, it predicts the other one. And this doesn't only work like that for this particular network for a subject-verb agreement, but interestingly also for gender. So this is something which may be interesting also for the people who are generally looking at biases, because we know also that these models reflect the biases that are in corpora. It seems that this model, if it has no information, it predicts that a pronoun should be male. And only when it has some information that it should be female, it predicts female. So in other words, predicting a male pronoun is not causally related to a male referent, whereas predicting a female pronoun is. Yes, let's try to make the next coffee break in time. So, my conclusions here. We can study black box neural networks with behavioral experiments. So these are the types of experiments that I presented in the beginning, where we check if a model can predict the right outcome, but also later if we check if a model can predict a verb with the correct number. But we also have quite some techniques available to study their representations, and this is really a booming field. The stuff that I mentioned to you, that I put it here, diagnostic classification, ablation studies, contextual decomposition. This is just the tip of the iceberg. Many more things are coming up also now. Neural networks seem quite capable of modeling hierarchical structure, even if the data that they deal with is messy, like natural language. And I wanted to end with saying, so when I started this exercise, I was hoping that getting more information about how these networks are doing it, which, as I said in the beginning, have some similarities also with the human brain, that this would give me also some information about how humans are doing it. Now, until now, this didn't unfortunately give me this information yet, although we are at this very moment running a study also with humans where we're checking if maybe there are also these two conflicting mechanisms to represent short distance and long distance numerosity. So in that sense, I think this is one of the first things that comes out for me, where we can actually, using neural networks, formulate some concrete hypotheses that we can then also test in humans. But I wanted to just end with a note that said I'm looking forward very much to the next step, where we can really reconnect all these findings here with what we know about human languages. Thanks also to my collaborators. I didn't have as many as Carl, so I could put also some pictures. My PI is, as was already mentioned, is Willem Zuidema. He is actually the reason also that I'm here today, so especially thanks to him.
Questions?
Thanks. Super interesting. I do the human side of this. So a question about the conclusion you drew about what's happening to the number of information.
Mm-hmm.
So, and it may have been answered by your ablation study that I didn't fully follow. So, just because I got it. So, you said there's a difference between, you concluded that the number of information is moved.
Yeah.
So there's some different state while you're going through the relative clause. And the evidence for that was a difference between the predictive classifier on the subject versus subsequently, right?
Yeah.
I guess, so I'm wondering about that. Does that, how clearly does that show that information is actually being moved? Because even if you weren't moving the information, you have to distinguish is the subject, is the numbered item right in front of me right now versus it's something that's independent, separate from that? I guess, wouldn't you get the same result even if you're not moving it?
Isn't what you're saying some version also of moving it? So you're saying something, if I well understood, you're saying I'm getting in that something is singular, but then afterwards I need to represent both that it's singular and that I do not need this information at this point.
That's what I was wondering as I was listening to it. So I think, I thought what you meant by moving is something more than that. And so that was maybe also clear in the number language
Yeah,
you talked about, right? Because, and that would make a difference, for example, to, is that subject number still active in some fashion when you're working through the relative clause, or is it like in a box where it's not going to interfere with that?
I don't think that it's, so I don't think that it's neither in a way. So as we can see here, it's not that we cannot find this information anymore, because we can predict it with a very high accuracy. We will have above 90 there. It's just that the way that we find it is not the same as that we found it in the first step. So this is the evidence that I'm taking for it being moved. So say that we would actually have a bunch of boxes, or we would just have 3 boxes, and say when the subject comes in, I put it here. Then when I'm learning where to find the subject, I'm going to look in this first box all the time. But if that doesn't work, it means that this information is not in the first box anymore. So it can be that it's still there, but maybe it's in the second box.
I guess, so maybe, would you make a prediction about the following thing? So if you have a verb inside the relative clause,
Yeah.
which itself has to agree a number, what would the impact of the main clause subject be on that? Have you tested that?
No, so in this particular study not, but knowing from the other study that I've done with the ablation, it seems really to be that there is in fact a short distance and a long distance mechanism. And the prediction that quite directly follows from this is that if you have more than one attractor and also more than one subject-verb relationship in this embedded clause, things go wrong. And you see indeed, I don't have this particular information here, but you see that what the model then does at the end, it's not on chance. It actually systematically predicts the wrong thing, because the long distance one is busy with this long distance thing in the middle, so it got overwritten. The short distance one was busy with the one that was even shorter. And since these are the 2 mechanisms that it has, there is nothing anymore to represent the outer dependency. So yeah, but maybe if it's still not clear, we can have a chat about it later. Thanks.
More questions?
Great talk, thanks a lot. In your early part of the talk, you had the 2 mechanisms to solve the simple arithmetic equations, the, let's say, the recursive and the cumulative one. When you generalize the problem, including multiplication and division, would you need a hierarchy of the operations, or would one additional layer just be sufficient? And
Yeah,
how
that's a
does
good
knowledge
question.
deal with that question?
I never looked at the multiplication because it puts on some other problems, right? So for the plus and the minus, you can still compute things pretty much on the spot, right? The moment that you have multiplications, you kind of cannot do that anymore, because there is no way that you can know what is the impact of a multiplication at the beginning. So everything may change at the end. So I think that what levels of hierarchy you need to represent particular levels of hierarchy in your problem, it's not a solved problem. So I've been doing some other experiments with other artificial languages where we have even a more clearly defined hierarchy, and there we're not only looking at recurrent models, where recurrent models usually they stick with just 2 layers. So whether this is because the 3rd layer doesn't help anymore, or because these models need to self-learn, and maybe it's just very difficult to learn the 3rd layer, I'm not sure, but that is just, when you look at the literature, these models are usually not very deep. Recently, there has been another class of models, they are called self-attention models, or transformers, and they are very, very deep, and for them, really also adding more layers helps. So the connection between hierarchy and in the problem and hierarchy in the network, I think it's an unsolved problem that people are looking at.
More questions? Okay, so first of all, let's thank our speaker.